Welcome everyone. Today I want to talk about our approach for low-cost GNSS systems to address the problem of field data capture in precision agriculture. Fieldwork in precision agriculture usually involves data capture from different equipment such as spectroradiometers, solar luminance sensors, chlorophyll sensors, and GNSS receivers, as well as crop sampling. So this work usually involves significant human effort. 8 fiberglass devices were built in a 45 cm square pattern. The design was made in the form of black and orange squares. The size of the GCP marker was selected to make sure it covers at least 30 pixels in an UAV image acquired with a MicaSense red edge sensor at a height of 100 meters above ground level. The hardware subsystem consists of a single board computer, a low-cost GNSS receiver, and a power supply. The Raspberry Pi Zero was selected for the configuration and management of GNSS information, and the new blocks receiver was selected, as well as a 5-volt power bank with a 5000 mAh. The method that was selected to make the connection to each of the GNSS GCP was Wi-Fi. To remotely access the configuration of the control point, is necessary to use a protocol such as virtual network computing or VNC to communicate with Raspberry Pi. To remotely access operating system files and files generated when tracking at a given position, it is necessary to use a file transfer protocol to the file system of Pi Zero. When the GCP marker is turned on, an open Wi-Fi network is automatically created. The user must connect to this Wi-Fi network and open any VNC client on his computer or smartphone to connect by graphic environment to the GCP configuration software. Once the data capture is completed, the user must stop the tracking. Then the user must enter the FTP service, and the tracking file will be found for download. Once the download is complete, the GCP marker can be turned off. 8 GCPs were built to test the ground control system and conduct the experimental survey in precision agriculture projects. 2 different test areas were selected. The first covers 20,100 square meters. It was a potato experimental crop located in the municipality of Mosquera, Colombia. The second area covers 17,100 square meters, and it was a commercial potato crop located in Madrid. Estimate of relative accuracy was performed by including the processed X, Y, and Z GCP coordinates into the photogrammetric processing of the captured UAV imagery. For the Mosquera's dataset, 5 GCP coordinates shown in Table 1 were used to achieve the geometric correction of the model, while 2 GCPs were used as checkpoints. See it in Table 3. The minimum root mean square error for the checkpoints table corresponded to the Z coordinate, while the maximum root mean square error was obtained for the Y coordinate. The average root mean square error was 0.25 centimeters. For the Madrid's dataset, 5 GCP's coordinates shown in Table 2 were used to achieve the geometric correction of the model, while 3 GCPs were used as checkpoints. You can see it in Table 4. The minimum root mean square error for the ground control points table corresponded to the X coordinate, while the maximum root mean square error was obtained for the Y coordinate. The average root mean square error was 121 centimeters. Integrating low-cost GNSS receivers to ground control points allowed to considerably reduce the amount of field work that currently must be done. Relative accuracy of the proposed ground control points seems to be high enough for many farming purposes, although it is always advisable to validate the accuracy of the positioning by using conventional GNSS survey with high precision equipment before conducting a survey. The main advantages of the proposed development are the low cost and the fast data capture in field. The proposed improvements to this development are to use dual frequency receivers and a marker design with IP67 standard for wheat and dusty areas.